This is AQA A-Level Chemistry. We are on the alcohols topic, and this is part 5 of 5 in the series that cover the alcohol topic. As always, I'm going to recommend that you try the activities as you go and see how you do with them. We're going to start off straight away with a huge part of the topic, and that is the test for aldehydes and ketones. Now, we do have some specific ones. We are going to avoid using acidified potassium dichromate 6 in this point. So I am going to tell you that we are considering tollens and fehlings. Have a go at filling in as much information about these as possible. Think about the reagents that we use, the conditions, the observations we make with an aldehyde, the observations we make with a ketone. And in the first instance, we have reagents. Tollens, we have silver nitrate and ammonia. Both of those are needed. And it's the Ag plus ions that are really important, actually. And in fehlings, we have fehlings 1 and fehlings 2. Now, within there are copper 2 ions that give the really rich blue colour. And if it helps you to remember, fehlings essentially works in exactly the same way as Benedict's solution in reducing sugars. That might help you to remember the observations later on. In terms of the conditions, we warm them. We do these in a water bath. And then we look at the observations. Now for tollens, we will get a positive result. A silver mirror is formed on the surface of the test tube. The Ag plus is reduced to Ag. Now by reducing it, it's acting as an oxidizing agent, and we are oxidizing the aldehyde to become a carboxylic acid. Similarly, in fehlings, we have got the blue solution going to a brick red precipitate, so a very different observation, but that is coming from copper 2 ions being reduced to copper 1. They're reduced, which means they're an oxidizing agent. They are oxidizing the aldehyde to become the carboxylic acid, just like we saw where an aldehyde could be oxidized to a carboxylic acid with acidified potassium dichromate 6 under reflux. Now we also know that secondary alcohols can be oxidized to a ketone, but they can't go any further. So actually when we use tollens and fehlings, which are quite mild oxidizing agents, we get no visible change. So we get to see how this serves as a test. Positive test, aldehyde. Not a positive test, ketone. Same for both of them. Now in terms of equations, we're moving on slightly here actually, and we're looking at combustion of alcohols. Have a go at writing out the equations for the combustion of alcohol. First one, we've got ethanol plus oxygen, and it is going to make CO2 and H2O. I then just need to balance it. I'm going to balance my carbons and balance my hydrogens, and then I'm going to be very careful in balancing my oxygens. I've got 4, 5, 6, 7 oxygens over here. Remember, I've already got 1 O in the alcohol, so I need 3 O2, not the 3.5 that commonly comes up as an error. On the next one, propan-1-ol, I'm going to draw out the structural formula here, CH3, CH2, CH2OH. And once again, I'm going to balance my carbons. I've got 3 of them, so that's 3 CO2. I'm going to balance my hydrogens. I've got 3, 4, 5, 6, 7, 8. That means that I've got 3 CO2 and 4 H2O. I've got 6 oxygens, 10 oxygens on the right. I've got 1 already in the alcohol. That leaves me with 4.5 O2. Pentan-1-ol, I'm going to draw out structurally again, 5 carbons, so I'm going to make 5 CO2, 12 hydrogens, 6 H2O. I've got 16 oxygens. I've got 1 used already, so that's 15. I need 7.5 O2. And finally, hexan-3-ol. I am going to balance that in exactly the same way. 6 CO2, 7 H2O, and 9 O2. Taking into consideration there's already an oxygen in here. We're then going to move on to another key part of this topic, but very different to the 2 sections within this video. Elimination mechanisms. Now, we can look at this as an equation. Have a go at writing an equation for the dehydration of ethanol. And what you will see is that the ethanol becomes ethene and we've lost the water. The fact we're making water means we've removed water from the ethanol. That's why it's dehydration. But we also need to know this mechanistically, so have a go at doing the mechanism. And if you draw it out, we have got our propan-1-ol, and I've got an H plus ion, which I'm going to have my lone pair, electron rich, going to my electron deficient H plus, so my curly arrow goes in that direction. Now that leaves me with an unstable molecule. I've got an OH2 with a positive on the oxygen. So there are two more steps here. One is that the water is lost, it's gone. Two, we lose an H on the neighbouring carbon, and that comes in and creates the double bond. We get ethene and we get water. An extra little question here. Think about which alkene product we would get in the dehydration of butan-2-ol. I'm not going to say how many there are. So let's start by drawing out butan-2-ol and look at where we might lose an OH, that's after an H has been added and it's lost as water, and a neighbouring H. It could be those circled in red or those circled in green. Now if it were those circled in green, that would give me but-1-ene. I've got my first answer. If it were the red H and OH, it would be but-2-ene. So your immediate thought there might be that there are two potential answers. But you've got to remember your knowledge of wider organic chemistry. But-2-ene could be E or Z. So there are actually three different potential products that could be made within that reaction. And to finish off this video and this topic, these are really important. You have got to remember the conditions in which alcohols are dehydrated. 600 Kelvin, hot concentrated sulfuric acid, and we pass the vapour over aluminium oxide. That's the end of the video. Thank you for listening and goodbye.